we can set up equations involving vectors. These equations turn out to be another way of writing systems of linear equations. A vector equation is an equation of this form. Here, C1, C2, up to Cn are unknown scalars. And these vectors, V1 up to Vn and B, are all known. And your goal is to find the scalars C1, C2 up to Cn that make this equation true. To see how this relates to systems of linear equations, let's rewrite this so that the components of these vectors appear. So here's our vector equation. We can do all of this scalar multiplication like so. And now we can do this addition to get to this equality. Now, when our two vectors equal, well, to be equal, this first entry here has to equal this first entry here. This entry here has to equal this entry here. And so on down the line. And all of these equations have to be true at once. So this is a system. Now, I think it can be a little overwhelming to look at these things in generality with all of these n's and m's floating around. Let's look at an example to help clarify this. This vector equation is the same as a system of linear equations with unknowns C1, C2, and C3. The first equation is 1C1 plus 3C2 plus 1C3 equals 1. And then the second equation, we see 4, 0, 6. 4C1 plus 0C2 plus 6C3 equals 5. Then 7C1 minus 1C2 plus 1C3 equals 7. And the good thing about this, of course, is that we know how to solve systems of equations like this using Gauss-Jordan elimination. So we don't need to learn a separate trick to solve vector equations. We just rewrite them as systems of linear equations and solve them that way. I went ahead and did that off camera. C1 is 28/29. C2 is -3/58. C3 is 11/58. So vector equations are solved using Gauss-Jordan elimination.